Hi everyone, welcome back to Mind and Maths with Amina. In today's lesson, we're going to talk about the saddle path equilibrium in difference equations, a concept that becomes especially important when we study dynamic economic models such as investment, consumption, or capital accumulation over time. When a system has two variables that evolve across time, we often draw phase diagrams, which I will cover in my next few lectures. To understand, we need to draw these phase diagrams to understand how the system behaves. But sometimes the equilibrium is not stable at all in all directions. So some deviations may push the system away unless it lies on a very specific path. That specific path is what we call the saddle path. By the end of this lesson, you will be able to identify when an equilibrium is a saddle point, understand why only one trajectory leads through the system back to equilibrium, and trace the stable path using a phase diagram. So let's take this step by step and really understand the intuition before the mathematics. In the previous lesson, I made this 2 by 2 system and we solved it using diagonalization, and this was the solution. I stated in the previous class that the eigen values lambda 1 and lambda 2 need to lie between a minus 1 and 1 for the system to be stable. If these values exceed 1, so suppose if both the eigen values exceed a 1, then we have a system which is completely unstable. However, we can create a saddle path if suppose one of the eigenvalues is stable and the other one is unstable. So in this scenario, we can find a saddle path. So let's suppose that lambda 2 is the eigen value which is causing the instability. So what we're going to do is, since lambda 2 is causing the instability, we want to make this impact redundant. So what I'm going to do is that I'm just going to impose a restriction on the constant being multiplied by it. So basically what I'm going to do is I'm going to impose the value of n naught being equals to a 0. So let's go ahead with this. Let's impose this. So moving on, this was my system. Let's bring it down here, and first let's convert it to a matrix, a system, and put it at time 0. So I'm going to have a y naught here, a z naught here, and I'm going to have a v u 1 1, and my unknowns are going to be a mu naught n naught. We know anything power 0 is equals to 1, so therefore I know lambda 1 power 0 is going to be equals to a 1, and lambda 2 power 0 is equals to a 1. So therefore we're just left with this. Okay, and then we have a z bar, a y bar, and z bar. Remember, I want to find the value of these two, and I want to impose the restriction of m not being equals to 0. So let's find this. I'm just going to first take this into the subject. So I have a ax is equals to b format. So I'm left with y naught minus y bar and z naught minus a z bar. Okay, let's just, you can use anything. You can use Gaussian elimination. You can use the Cramer's rule, and you can use the inverse. I'm going to use the Cramer's rule because I find it quite convenient. The value of m naught is going to be the determinant of y naught minus y bar, z naught minus z bar, u1 over the determinant of v1 u1. In the numerator, we're going to have a u naught minus a u bar minus u into z naught minus z bar over a v minus a u. So uh, we wanted n naught to be equals to 0. So let's find n naught as well. N naught is going to be v1 z naught minus z bar. Oh, this is down here. And y naught minus y bar, the determinant of this divided by the determinant of the main matrix. So this is the Cramer's rule. We take the determinant, we're left with v into z naught minus z bar minus y naught minus y bar over a v minus a u. So we wanted to impose the restriction that n naught is equals to a 0. So therefore, this whole expression right here becomes a 0. So we're left with y naught minus y bar is equals to v z naught minus z bar, and basically this gives you the this is the equation of the saddle path. So what I can write this as yt is equals to y bar plus v z t minus z bar, and this right here is going to be the equation of my saddle path. Okay. What about the value of n naught? So the value of n naught was this. I'm just going to cut paste it here. And then what I'm going to do is I'm going to substitute the saddle path equation into it. So this is the saddle path. I'm going to substitute this into this. So what am I going to be left with? I'm going to have a v z naught minus z bar minus v z naught minus a z bar over oh, that's confusing. That actually gives me a 0. So maybe I did something wrong. Let me recheck. Let's not panic. Going up, this was y naught minus y bar. Yeah, we got this one right. M naught, we replace this over here. This stays there. We did this. Okay. Then we wanted this. So I'm going to replace the second column with this. We did B, did this, and then we had that. And then I just put it equals to 0. We wanted n naught equals to 0. because we were assuming lambda to give us instability. So, what's happening here? If I put this equals to 0, I get this equation. Yeah. And when I put it in, that's ridiculous. See, it's so funny. I was putting it back in N naught. We were supposed to find M naught. It's right here. The disadvantages of taking a class where you're speaking by yourself. Now, if I had my students, they would have told me, Miss, you've written it incorrectly. Okay, so now I'm going to substitute this right here. Sorry guys for the silly mistake. I'm just a human being as well. So let's not panic and try to get the right solution in the end. Okay, we have a v minus a u here. And we have a z naught minus a z bar here. And what we're going to do now is this is going to cancel out. So I'm left with a z naught minus a z bar. So there we have it. That's my solution. So this is the value of m naught, and this is the value of n naught. So our final equilibrium is, so these were the equations where we had a stable equilibrium, but now we have a saddle path. So what we're going to do is that we're just going to substitute these saddle equilibrium values right here. We know that n naught was actually, we imposed it to be a 0. So we're just going to remove that altogether from the equation. So this disappears, right? We don't need it anymore. And we just found the value of m naught, which is a z naught minus z bar. Voila. So happy to see this. And this is why mathematics gives me a lot of joy, because when you do end up with the right answer, it's quite thrilling, I feel. Okay. Even if we make a little tiny mistakes along the way, it's fine. Okay, this goes here, and we have this, and that's it. We're done. So this is the saddle path equilibrium, and we're done with this. And what we can do is we can show what a saddle path looks like on a phase diagram. So for instance, I already drew this. Suppose we have in a saddle path, we have a positively sloped LM curve, but we also have a positively sloped IS curve. I'll show this later, that for a saddle equilibrium to exist, we need IS curve which is actually steeper than the LM. So I've given a diagrammatical insight into what a saddle path might look like. So if you can see, the economy does converge to this point A, only if it's on the saddle path. Otherwise, it's kind of diverging away from the equilibrium. So it's diverging away from the equilibrium over here as well. So like this, like this. So the saddle path is a unique path where the economy basically just easily converges to uh, an equilibrium. Otherwise, it won't. So I'm just going to give an closing summary, like a conclusion line to this lecture, and just basically the key takeaway from today is that a saddle path equilibrium is stable only along one precise path which I showed right here. So this is the one precise path Any deviations away from this path sends the system diverging, which is why dynamic adjustments, this is the uh, divergence that I'm talking about. So this is why dynamic adjustments in these models requires expectations or behaviors to be aligned exactly with the stable trajectory. If you found this helpful, take a moment to pause and try drawing the phase diagram on your own. Teaching yourself through repetition is where mastery comes from. I feel that. Thank you for joining me today. Stay consistent, stay curious, and I'll see you in the next lesson, inshallah.